All right, welcome to 2.3.5, featuring October, who is sitting on my notes. Anyway, so 2.3.5 is going to be talking about one-sided limits and piecewise functions. So remember a couple things about one-sided limits. Specifically, hold on, I actually don't remember the first thing I want to remind you of. Specifically, we're going to start with an example. All right, perfect. Example number 5. Example 5 says evaluate with a table. Yes, all the way back here. Remember evaluating limits with tables? Part 1 is the limit as x approaches 3 from the right of the square root of x minus 3. So we make a table and say, okay, let's look at some x's. Let's look at some function values. And let's have x get really close to 3. We usually do it something like this. All right, so this is the function square root of x minus 3. We can use Desmos to make this a little quicker for us. F of x equals the square root of x minus 3. And say, okay, what's f of 3.1? I'll say it's about 0.3162. Let's plug in, let's add another 0. Let's get even closer to 3. All right, it's 0.1. Let's get even closer to 3. 0.0316. Let's get another one. We need more information here. Let's get even closer to 0. Whoop. Closer to 3. 0.01. And in fact, every time we add 2 more zeros, we get to add 1 more 0 here. All right, if we added 2 more zeros, compare these two, we got to add 1 more 0 here. There's actually a really interesting reason for why that is, but I don't want to go too into it now. But the important thing, right, is that x is approaching 3 from the right, or above 3. This function is approaching 0. So our intuition, we're not proving this right now. The intuition from before is we'd say, all right, it looks like this is 0. What about part B? The limit as x approaches 3 from the left of the square root of x minus 3. We're going to do the same thing. Let's make a table. This time we're going to approach from the left of 3. So maybe 2.9, and then 2.99, and then 2.999, etc. So we go over here and say, all right, what happens when we plug in 2.9? Oh. What about 2.99? This is not none of these are in the domain. What is a domain of a square root function? The domain of a square root function is all of the inputs that have the inside, the radicand, be greater than or equal to 0, non-negative. Well, all of these are undefined because if we're approaching 3 from the left, right, 3 is the end of the domain. Right, the domain is 3 to infinity for this function. So we can't approach it from the left. This limit does not exist because the function is not defined from that direction. Okay? So be careful with one-sided limits and two-sided limits in situations like this. Okay? If the function is not defined, you have to be aware of that. Think about your domains. This is something that could happen here. All right. And again, you can see this graphically as well. 3 is right here. And as we approach from the right, yeah, those y values are getting close to 0. But we can't approach this point from the left. There is nothing to the left of this point. Similarly, if we were looking at like a logarithmic function, right? If we talked about the limit as x approaches 0, As x approaches 0 from the right, this limit is negative infinity. This function shoots down to negative infinity. But we couldn't talk about a limit as x approaches 0 from the left because there is nothing to the left of a logarithm, or nothing left of 0 for a logarithm. All right, so that's something else where it could pop up. Something else about one-sided limits. Remember from the last section that the limit as x approaches a of some function exists if, and only if, the limit as x approaches a from the left is the same as the limit as x approaches a from the right of that function. So for a two-sided limit to exist, remember, both one-sided limits have to be the same. So in this last example, I didn't ask about it, but if I did ask a part C, that said, what is the limit as x approaches 3 of this function? The answer would be does not exist. For this limit to exist, this limit would have also had to have been 0. So we need the limit to be the same from both directions for a limit to exist. All right, so we're going to use this property when we talk about piecewise functions. Example 6. Let f of x be a piecewise function. Let's have it be the function 4x minus 3. And it's only 4x minus 3 when x is less than 2. And if x is at least 2, then this is the function x minus 3 squared. Piecewise function says, depending on where you're at in your domain, depending on what your input is, I'm going to give you a different rule. And in real life, right, piecewise functions pop up. It's like, maybe if you buy a certain number of items, you'll get a discount. That's a piecewise function. Otherwise the cost is just linear, right? If everything's $2, you just multiply how many am I buying? $2, and you get the cost function. But if you get a discount for buying a certain number, it's going to be a piecewise function for your cost value, stuff like that. Discounts, special rates, tax brackets, etc. are all piecewise functions. So part A, I want you to find the limit as x approaches 2 from the left of this function. So one-sided limits are really, really important for piecewise functions because as we're approaching 2 from the left, right, that's like 1.9, 1.99, 1.999. As we're approaching 2 from the left, we're always using that top piece. If we're to the left of 2, then x is smaller than 2. So just maybe make a comment over here. Right? As x is approaching 2 from the left, f of x is equal to 4x minus 3 only, right? We're only using that piece. Because as x approaches 2 from the left, x will be less than 2. So this limit is actually the same as the limit as x approaches 2 from the left of just 4x minus 3. We don't have to worry about the other piece in the piecewise function because we're only looking at input values that are really close to 2 from the left. Input values that are really close to 2 and just a little bit smaller than 2. That's how we work with piecewise functions and limits. All right, so this is a rational function. This is a polynomial. Direct substitution works here. You can just plug it in. 4 times 2 is 8. 8 minus 3 is 5. That's the limit from the left. Part B, what's the limit as x approaches 2 from the right of this function? Well, by the same logic, if we're to the right of 2, then we're always on this second piece. So the limit as x approaches 2 from the right of that second piece. And again, this is a polynomial as well. Direct substitution is going to work here. Plug in 2, get 2 minus 3 is negative 1. Square that is positive 1. So immediately, you might know where I'm going with this. What is the two-sided limit? You should have an idea. Two-sided limit. No, I'm not going to go on. All right, I'm not going to scroll off. The two-sided limit, that's going to be part C. What is the limit as x approaches 2 of this piecewise function? Well, from the left, it's 5. From the right, it's 1. Two-sided limit does not exist. All right, because they're different. Right, because 1 is not the same thing as 5. That's how you evaluate piecewise functions and limits. So there's one other thing that can kind of pop up in this one-sided limits subsection, and that's what we're going to talk about in example 7. It has to do with asymptotes. You're going to have to remember a little bit from your pre-calculus, which if you don't remember, that's fine. We'll have an opportunity to review it together, and you can always ask me questions about it. Evaluate the limit as x approaches 2 from the left of this new function, x minus 3 divided by x squared minus 2x. And again, direct substitution is great as long as everything's defined everywhere and we're not dividing by 0. So let's try that. Again, you have to be a little careful with direct substitution for one-sided limits and two-sided limits. Make sure things are defined, right? You can't use direct substitution here because on the left, it's not defined. But here, this is a rational function, so it's going to be defined almost everywhere. So direct substitution would give us, all right, that would give us 0 in the denominator. We can't use direct substitution here. So can we cancel, right? We had those 4 techniques. Factor and cancel, multiply by the conjugate, simplify in other ways, simplify complex fractions. None of those apply here. Because if we factor, right, let's factor anyway. Even though it's not going to help us, it's good practice, and it's a good thing that you should be checking. We factor, we're left with an x times an x minus 2 in the denominator. So nothing simplifies. We are still dividing by 0. Direct substitution is not going to work. We have to use what we know about vertical asymptotes. Okay? So this is a vertical asymptote. And the reason why we know it's a vertical asymptote is because there's a factor. It's a rational function and a factor of x minus 2 in the denominator that says there's going to be a vertical asymptote at x equals 2. Vertical asymptote at x equals 2. We then look at the multiplicity of that vertical asymptote. Multiplicity is that exponent. How many times does this factor appear? The multiplicity of this is odd, which means that from the left, it's going to be positive or negative. And from the right, it's going to be the other kind of infinity. So it's going to be different on either side, just like 1 over x. So we only care about how does this behave from the left. It's either going to be positive infinity or negative infinity. So it's equal to some kind of infinity. To figure out whether it's positive or negative, we just plug in a point, or you could graph it. So we just plug in something really close to 2, a little bit below it, and we can get our answer that way. All right, so if we call this, let's call this f of x. F of something a little bit smaller than 2 tells us whether it's positive infinity or negative infinity. And again, I don't usually write the plus here, but you can. Again, if we plug in 1.999, just use a calculator. 1.999 minus 3 divided by 1.999 times 1.999 minus 2. And we are indeed going to get about positive 501. Let's round. So we knew it was either positive infinity or negative infinity. We plugged in something really close to 2 on the left of 2. We got positive. That's going to be positive infinity. And because of what we know about here, that means that from the other direction, 2, as we approach 2 from the right, it would be negative infinity. Let's graph it and verify our answer. Y equals x minus 3 divided by x times x minus 2. As we approach 2 from the left, it does shoot off to positive infinity. As we approach 2 from the right, it does approach negative infinity. This is a rational function. Okay? And again, to kind of re-emphasize a small technicality, when we say that the limit is equal to infinity, the limit technically doesn't exist. We just write that it equals infinity because that's a way of describing the behavior. But a limit equaling infinity is different than a limit equaling 2, for example. Small subtlety there that's not really going to impact you in this course, but it might impact you in future math, depending on how high you're going up the math ladder. Not even a math ladder. This is the end of the video. It's just rant time now. It's not even a math ladder. Mathematics is like a giant tree, like a giant bush. Like you climb the trunk for a little bit, and then there's so many branches, you just go in every direction. And a mathematician in this branch over here, combinatorics, has no idea what a mathematician in complicated partial differential equations or something is going to be talking about. Like they can go down their branches and then find a place where they can meet up, but usually one mathematician, one field is not going to understand really the research of another mathematician in another field. But anyway, that's unrelated to calculus, but it's interesting. If you like talking about mathematics, I will talk about this some more. As I said, this is the end of the video though, so take it easy and get some homework problems done. And ask me if you have questions. Bye-bye.